Every year since 2018, astronomers have spotted a mysterious blue flash in the sky. It is one of the brightest phenomena in the universe, an explosion that makes the average supernova look like a faintly lit candle in the distance. Some have been spotted closer to us, and others, billions of light years away. They look similar enough to one another, but no one knows what they are, or what causes them. Through rigorous observation and analysis, astronomers began decoding a pattern and formulating a tentative but plausible theory. Until, in 2023, they saw something that left them completely baffled. These explosions are called luminous fast blue optical transients, and there's simply nothing else like them out there. Join me today as we dive into the mystery of space's brightest explosions, how they were discovered, and why they keep stumping scientists again and again. What are LFBOTs? Being such a recently discovered event, the data we have on luminous fast blue optical transients, or LFBOTs for short, is minimal. The first LFBOT ever detected was identified just 6 years ago in 2018. And we've only witnessed a handful of them since. As so little is known about them, it makes agreeing on a universal definition a little tricky. For now, what scientists do all agree on are some common characteristics these LFBOTs seem to share. So far, they all display a predominantly blue emission, very high optical luminosity, and are bright in X-rays, ultraviolet rays, and radio waves. They are also very fast, as their name indicates. LFBOTs go off like a cosmic camera flash. They reach peak brightness and then dim very rapidly, usually in the space of hours or days. As you might know, a supernova follows the same pattern of brightening and then dimming, but this dimming takes weeks or months. This short-lived nature of LFBOTs makes them difficult to spot and study. So, how did we manage to capture such an elusive event? The ATLAS. NASA's ATLAS-HKO telescope in Hawaii is part of an early asteroid impact warning system that scans the entire sky several times a night for moving objects. On the 16th of June 2018, ATLAS-HKO was performing its routine scan when it captured something very unusual, a flash, 100 times brighter than a regular supernova, that disappeared within days. The scramble was on. Scientists immediately started analyzing the data to understand what they'd just seen. They pinpointed the explosion as coming from the Hercules constellation, some 180 million light-years away. Officially designated AT-2018-HKO, the event was affectionately nicknamed the HKO, after the last 3 letters in its name. Once located, it was quickly classified as a Type I supernova. This kind of supernova, also known as a core collapse explosion, is formed when massive stars collapse under their own gravity. But something about this particular explosion didn't quite fit. When taking a closer look at the HKO's emission spectrum, it didn't look very typical for a Type I supernova. It had unusually broad emission lines, and very weak helium lines. Scientists thought it appeared more reminiscent of a Type ICBL supernova, and so it was quickly reclassified. However, the more scientists pored over the data, the more surprised they were by what they found. Whatever this explosion was, it started to look less and less like a supernova. At least not the kind of supernova we'd expect. For starters, it appeared out of nowhere. This blast went from inactive to peak luminosity in just a few days. Like we mentioned earlier, supernovae usually take a few months to reach their brightest, and dim again at a similar pace. Not only that, it was registered to be 10 to 100 times brighter than an ordinary supernova. Also, everything about the way it exploded was wrong. When supernovae explode, they tend to release their energy in a spherical shape. We know now that the shockwave sent out after a supernova can be aspherical, due to the presence of strong magnetic fields which can distort the shape of the initial blast. However, upon closer inspection, this mystery explosion did not even explode spherically. The researchers themselves called it the most aspherical explosion ever seen. Soon enough, other theories were being put forward. Some thought the HKO could be a monster black hole shredding a passing star. Others suggested it was a supernova that gave birth to a black hole or a neutron star. But let's step back for a moment. It's really hard to draw any conclusions when you only have one of something. As the saying goes, once is an anomaly, twice is a coincidence, and 3 times is a pattern. What researchers really needed was a bigger sample size, more instances of this kind of explosion, so they could compare observations and deduce any patterns that might arise. Luckily, it didn't take long for scientists to get their eyes on a second similar explosion. A few months later, in September 2018, the cosmic camera flashed again. And again, for a third time in 2020. Keeping in the tradition of pulling animal nicknames from the last three letters of their official names, we had the beginnings of a LFBOT zodiac. The cow was joined by the koala and the camel. And just like that, they had data on three separate LFBOT events. They could start hunting for patterns. When analyzing the cow, koala, and camel, one of the first things that stood out to researchers was the location of these events. Even though they all happened in different parts of the universe, each blast was registered as coming from inside the spiral arm of a galaxy. At first, this information emboldened the initial theory that LFBOTs were just a type of core-collapse supernova. Let me explain why. The kind of star that causes a core-collapse supernova is a massive star, one of the biggest types of stars you can get. And as you know, the bigger the star, the shorter its lifespan. This means that these massive stars don't get the chance to travel very far before they die. It would make sense then that their supernovae occur very close to the star cluster where they were born. And what part of the galaxy is known for having such star clusters? Yup, the spiral arms. The exact place we saw all three LFBOTs. But just as researchers seemed to be making progress, something happened that caught them completely off guard again. Like the ATLAS-HKO in Hawaii, the Zwicky Transient Facility is a very wide-angle ground-based camera that scans the whole northern night sky every 2 days. In 2022, it detected another similar explosion. Except after the initial blinding flash, this optical transient started behaving rather strangely. Instead of exploding once and fading away in a few days like the other LFBOTs before it, the so-called Tasmanian Devil continued to produce short-duration bursts far longer than expected. What's more, each of these bursts seemed to be just as bright as the original explosion, which was very strange indeed. The Tasmanian Devil emitted more energy than hundreds of billions of stars, like our Sun, combined. Researchers were deeply puzzled, yet again. It was unlike anything they'd ever seen before in astronomy. Now, I know the skeptics among you may already be thinking, Alex, this has got to be due to some kind of technical error, miscalibrated equipment, a fluke in quality control tests, or a simple mathematical mistake. Indeed, the history of science is littered with scientists shouting eureka at supposed breakthroughs or discoveries, only to be deflated once someone checked their workings. But this is not one of those moments. The data was corroborated by 14 other telescopes around the world. They confirmed that the Tasmanian Devil did in fact pulsate a minimum of 14 times, the total number was likely much higher. Equally surprisingly, these mega-powerful pulses were only minutes apart. It looked to scientists like a star that kept dying and being revived again and again. If that's what it is, this strange phenomenon could provide brand new insight into the life of stars. So far, stellar life cycles have only been studied as snapshots of different stages, never as a continuous process. In short, even though the multiple bursts of light from the Tasmanian Devil were unexpected, there was still reason to suspect these explosions could have been a strange type of supernova, seeing as none of the observations directly violated the core-collapse supernova theory. But what came next, did? On April 10, 2023, astronomers picked up yet another big blue explosion with all the same characteristics as their LFBOT zodiac relatives. Except this one was not even close to where it was supposed to be. Unlike all the other LFBOTs before it, the Finch was not in the spiral arm of a distant galaxy. 3 billion light-years away from us, and 15,000 light-years from the closest galaxy, it stood solitary in space. It was in the middle of nowhere, and exploded between two galaxies. This was a huge blow to the leading theory. If these explosions really were the result of massive stars core collapsing, there's no way it would be happening in between galaxies. So, it was back to the drawing board for researchers. They came up with two new theories to explain what could have caused the Finch to explode where it did. The first suggests that the Finch could be the result of stars being torn apart by an intermediate mass black hole, a black hole that has 100 to 10,000 times more mass than our Sun. Except, the existence of these black holes has never been proven. Their smaller and larger relatives, stellar remnants and supermassive black holes, have both been confirmed to actually exist. But this middle child remains purely theoretical. However, should they exist, could they be responsible for this elusive light show? Astronomers have shown in simulations that stars can orbit intermediate mass black holes as many as 5 times before being ejected. With each orbit around the black hole, the star is effectively being ripped apart by losing more and more mass. Finally, the remaining stellar matter would be flung back out into the galaxy at speeds as high as 10% the speed of light. This would be consistent with the speed and brightness observed in LFBOTs, lending weight to this theory. One of the most likely places researchers would expect to find intermediate mass black holes is in globular star clusters in a galaxy's outer halo. Galaxies have halos that extend far beyond the main disk and bulge. They are most visible in spiral galaxies like our Milky Way. In our own home galaxy, the outer halo stretches some impressive 1 million light-years from its galactic center. Some scientists think it is possible that the Finch could have been located inside a globular star cluster such as this. If this is the case, and intermediate mass black holes do exist there, it could be plausible that the Finch was caused by these unusually sized black holes ripping up large stars. The second theory researchers put forward suggested that the Finch could have been the result of 2 neutron stars moving toward each other in increasingly tight spirals until they collided. This kind of event causes a kilonova, which is known to be one of the biggest stellar blasts in the universe. One telltale sign of a kilonova is the presence of gravitational waves, which come through as a hallmark chirp, caused by a rapid increase in frequency as 2 massive objects spin around each other, eventually colliding and merging. If we could find something like this when analyzing data from the Finch, it would lend strong credence to the neutron stars theory. However, as bad luck would have it, our chirp detector, the Laser Interferometer Gravitational Wave Observatory, was down for maintenance at the time the Finch occurred. That means we don't know if such gravitational waves were emitted, as we have no data on them. One thing we do know is that no gamma-ray burst was detected, which is something you would expect to see with a kilonova of this size. But remember, this explosion happened 3 billion light-years away. That's really far, perhaps too far for whatever gamma-ray data there might have been to be detected. All in all, none of this data can conclusively confirm or reject the neutron star theory. It's frustrating to bear witness to such an incredibly rare, new, and powerful phenomenon and not have the data to conclusively understand what is causing it. I guess patience is an underrated virtue for an astronomer to have. But they're not sitting on their hands, either. Scientists are already planning to use the powerful optics of the James Webb Space Telescope to carry out a search for any faint globular clusters in the same location as the Finch. This would hopefully clarify if they are on the right path with the intermediate mass black hole theory. In the meantime, other researchers are focused on broadening the sample size. The more LFBOTs we can detect, the more we will learn about them. The 6 we have seen so far have taught us some things, but we have a lot left to learn. The only way we are going to get a larger sample is to keep sweeping the sky with wide-field surveys like the ATLAS-HKO and the Zwicky Transient Facility. Scientists' hopes are pinned on the Vera C. Rubin Observatory, currently under construction in Chile, a telescope which will scan the entire southern night sky every few nights, which I've done a video about here. It is expected to be operational by 2025, and will be able to capture 10 times more light than all previous facilities. Follow-up observations with the Hubble and ground-based telescopes will help analyze more information, which could lead to more breakthroughs. LFBOTs are a super new phenomenon that we still don't understand well. Scientists themselves admit that the discovery of the Finch raises more questions than it answers. The more we learn about these bright blue explosions, the more they keep surprising us. All there is left to do is what hundreds of generations of astronomers have done for centuries before us: point our telescopes up to the night sky, watch, and wait. The universe might be full of mysteries. Thanks for watching. See you next time.